Implementation of a 4n-bit comparator based on IC Type 74L85 using linear threshold gate tunneling technology. Abstract. In this paper we will focus on the design of a 4n-bit comparator based on threshold logic functions using the specific behavior of a tunnel junction, i.e., the ability of controlling the transport of individual electron through a tunnel junction. We introduce an inverter based on single electron transistor, a novel design of an n-input linear threshold gate accommodating both positive and negative weights with one single tunnel junction and n+2 true capacitors, different gates like ANDs, OR, NOR and XOR. Every gates with their output waveforms are also introduced. All the time delays, their component values for different components are presented in tabular forms. Keywords: linear threshold gate, electron tunneling, comparator. 1. Introduction. It is clear for those who are involved in research in semiconductor technology that the ever-decreasing feature size and the corresponding increase in density of transistors facilitated many improvements in semiconductor-based designs. We are able to realize that such improvement will eventually come to an end. For ensuring further feature size reduction, possible successor technologies with greater scaling potential like single electron tunneling are currently under the investigation of researchers. Single electron tunneling based circuits are centered regarding tunnel junctions, through which individual electrons can be tunneled in a controlled manner. In our present era, high operating speed, low power consumption, and high integration density-based devices are financially indispensable in all the sectors of engineering and technology. Single electron tunneling-based device is one such equipment by which all Boolean logic gates can be implemented. It is a single electron which is adequate to store information in the single electron tunneling-based device in the atmosphere of 0K. Power being consumed in the single electron tunneling circuits is very low when compared with CMOS circuits. The processing speed of a threshold logic gate, TLG, will be nearly close to the electronic speed. The single electron transistor, SET, and LTG draws the attention of researchers, scientists, or technologists to design and implement large-scale circuits for the sake of the consumption of ultra-low power and their small size in different phases of applications. Tunneling events for TLG-based circuits happen when only a single electron tunnel through the tunnel junction under the proper bias voltage and multiple input voltages connected to the islands via small capacitors. For implementing a 4n-bit comparator circuit, LTG would be a best candidate for this case. Ultra-low noise is produced while tunneling an electron through the LTG-based circuit. Multiple input logic gates, and XOR, are implemented, and based on them, a comparator of 4 bits is implemented, and above all, with the help of this comparator a multiple of 4-bit i.e. 4n-bit comparator is presented in this paper. 2. Inverter. Almost for every complex circuit, an inverter 3, 7, 8 is essential. An inverter is depicted in Fig 1a, which is made up of 2 single electron transistors connected in series. The input voltage is directly coupled to the islands, indicating by small dots, of the SET1 and SET2 through 2 capacitors 1 and 2 respectively. The island of each set has a size smaller than 10 nm diameter of a superconductor metal like gold, and their capacitances must be less than 10 to 17 F. The output terminal 0 is connected to the common channel in between them and to the ground via a capacitor. To put down charging effects. For the inverter, the parameters values chosen are 1 equals 0, 2 equals 0.1 times, equals 9, 4 equals 110, 3 equals 12, 2 equals 12, 1 equals 110, 1 equals 12, 2 equals 12, 1 equals 174. And 2 equals 174, R1 equals R2 equals 100 KO. For simulation purpose, the value of C is taken 1AF in this work. The normal operation of the inverter is described as, the output 0 value will be high when the input voltage is low and 0 value will be low when the input voltage is high. To obtain this goal, we set the voltages, 1 equals 0, 2 equals 16 MV along with the tuning gate voltages. Both for SET1 and SET2 are applied. When is low, the SET1 goes in conduction mode and the SET2 in Coulomb blockade. This effectively connects the output to voltage and causes the output voltage to become high. Coulomb blockade interacts on the steady flow of current because whenever the high voltage, logic 1, is applied to the input, it causes to shift the induced charge on each of the islands of the two sets by a fraction of an electron charge and keeps the SET1 in Coulomb blockade 4, 5, 11, 14, 16, and the other one, SET2, in conducting mode. As a consequence, the output shifts from high to low. The simulation result of an inverter is presented in Fig 1d. 3 multiple input threshold logic gate. Fig 2 multiple input threshold logic gate. T. 4 threshold logic equation / function, TLF. A threshold logic function, TLF, is a Boolean function that can be implemented by using a single TLG. The TLF can also be called linearly separable. An unate function is a Boolean function represented by a formula such that each variable appears either in the positive or in the negative form throughout the formula. As the equations, 12, 16, 17, 18, 19, 20, and 21, have their variables either positive or negative for particular cases, so they are unate functions. Threshold logic equation for AND gate, F, AB, equals A.B. Threshold gate-based implementation. The threshold gate-based implementations of the Boolean logic gates have the same basic circuit topology and we will draw and explain them in the subsequent sections. The threshold gate is built up of a bias capacitance, a tunnel junction capacitance, and an output capacitance 0. The two input and OR gates contain two input true capacitors. For both the AND gates, the two input capacitors we are taking are C1P equals C2P equals 0.5. For positively weighted inputs. Whereas, for the NAND and NOR gates, two capacitors hold the values as C1N equals C2N equals 0.5. For negatively weighted inputs, every threshold gates is augmented with an inverter, Fig.1a, or 1c. The function of the inverter is to invert/buffer the output of a threshold gate. The logic function done by the buffered threshold gate is that the inverse of which is done by the threshold gate itself. For instance, a buffered gate implements the function. For the remaining part of our discussion, when we refer to a logic function such as AND or, we imply the logic function performed by the entire gate, i.e., threshold gate plus an output buffer. The parameters used for the implementations and simulations of different gates like AND, OR, NAND and NOR gates and other combinational or sequential circuits are given in Table 7.6, 7. 17 4-bit comparator. A comparator is a combinational circuit which compares two binary numbers for comparing whether one binary number is equal to, less than, or greater than the other number. We logically design a circuit which is having two input data A and B of 4 bits each, and three output terminals, 1 for AB, condition, 1 for A equals B, condition and 1 for AB, condition. When we are considering 4-bit comparison, the only Fig 13a is sufficient to manipulate the data in the input side to provide output. In this case the three cascading input terminals indicated by input AB, input AB, and input A equals B, are kept in don't-care condition. The only exception is that when the comparing data all are equal, we set input AB equals L, input AB equals L and input A equals B equals H. The input-output relationship is shown in Table 1. The marks times in the Table 8 indicate don't-care. Before cascading, when we are interested in what happens if we take the all possible inputs for cascading inputs, i.e., for input AB, and input A equals B, the input-output combinations we get from Fig 12a/Fig.12c is written in Table 9. From the table 9, we observe that when the comparing input data A and B are equal, the outputs, in the red color box, are not acceptable, because at the same time 2 or 3 output levels can be high or 3 output levels can be low for a comparator. Only one output level will be high and other 2 will be low for a comparator. As the comparator output condition levels are violating for the cases indicating by the red color box in table 9, so all the cascading inputs in the red color box will not be taken in consideration. So the modified table to be accepted when 2 or more 4-bit comparators are in cascaded connection is given in table 10. 18 8-bit comparator. After cascaded connection, 2 8-bit numbers compared by cascading 2 4-bit comparators U1 and U2 is shown in Fig. Point 13. The output of the lower order comparator, U1, I.E, when inputs A equals A3, A2, A1, A0, and B equals B3, B2, B1, B0, at terminals 5, OA equals B, 6, OAB, and 7, OAB, are connected respectively to the corresponding cascading inputs of the higher order comparator, U2. In the lower order comparator, U1, the A equals B cascading input, terminal 4, must be connected to high level input. And the other 2 cascading inputs AB, terminal 3, and AB, terminal 2, must be connected to low. The outputs of the higher order comparator, U2, will be the outputs of the 8-bit comparator. If anybody is interested in making a circuit for comparing more than 8 bits, then he/she can connect the circuit like Fig. Point 14 for comparing 4 times n bits, where n equals 3, 4, 5. So he/she can use a 4n-bit comparators. 19 Discussion. 20 Switching delays of LTG and set. The time delay or the processing delay for a CMOS logic gate like NAND, NOR, XOR is 1 to ns20, whereas the time required for tunneling through a single electron transistor, set, is approximately close to 4ns4, 5, 16, 18. The XOR gate using conventional logic circuits needs 16 transistors, whereas the same function can be implemented with the help of just one set. 3, 5, 6, 11, i.e. number of nodes can be reduced to 1 instead of 16. Assuming that error probability is 10 to 16, then the delay for the 2-input OR gate will be 2.28 ns, and similarly the other delays for the other gates used in implementing the IC chip 74L85 can be calculated and are all shown in Table 12. It is transparent that the LTG-based circuit is faster than the set-based circuit when equals 10-16. The comparison of delays for set and LTG gate-based circuits is drawn by a bar diagram in Fig. Point 16. 21 Conclusion. We discussed a novel design of threshold logic gates implemented in single electron transistor technology, where the basic operating principle is single electron transport phenomenon. A generic linear threshold logic gate implementation is elaborately discussed, and from which we have obtained a family of logic gates like NAND, OR. We have also derived the threshold logic equations for different logic gates. All the 2-input logic gates along with 3-input AND gate and 4-input AND/OR gates have been implemented and are verified by means of simulation using Simon. The number of elements like true capacitors, junction capacitor for logic gates, their delays, power consumed by them are shown in a tabular form, and their related curves or bar diagram are produced in due places. With the help of the different logic gates we have implemented a 4-bit comparator, and by this single comparator unit we have been able to build 8-bit or 4n-bit comparator. In single electron tunneling technology, we observe that the threshold logic gates are at least 3 times faster than CMOS-based logic gates. The operating temperature is kept very close to 0 K in real operation. At last we find that the implemented comparator providing the fan-out is the order of 109.